Well, welcome everybody to geohug, and I'm very excited for today's one. I'm thrilled that we have Hugh de Souza joining us today. So, Hugh is a consulting geochemist who retired as Director of Geological Services and Business Development with SGS Minerals in March 2022. He managed SGS geochemical, mineralogical, and diamond labs for more than 27 years and has worked on the development of new mineralogical and geochemical methods for mineral exploration. So, with all of his expertise, I cannot wait for him to take us through the evolution of gold assaying. So, this is going to be a fantastic session. I hope you all enjoy it. Get your questions ready because we'll open up the floor at the end. But yes, thank you so much, Hugh, for joining us today. It's amazing having you here.
Oh, thanks, Jessica, for the invite. I'm really happy to join you. I've seen a lot of good talks on your site, and it's great to be one of the speakers on this GeoHug.
Yeah, I'm thrilled to have you on. So it's very awesome. I was curious what got you into geology and geochemistry to begin with.
Um, I was born in Uganda, and it's had this incredible landscape, and all around, where I lived was mainly bush. And I'd go around and just trying to understand the landscape. So that got me interested in landscape and earth sciences, and I took an environmental sciences, earth sciences degree. And interestingly, a lot of the lecturers, professors there were working on East Africa. So I got interested in volcanic processes because they were also doing that for lunar and planetary studies. And a lot of our practical exercises involved looking at volcanic landforms.
Wow.
So eventually I got into a geochemistry master's, and then isotope geochemistry looking at Carboniferous volcanism in central Scotland. I moved up to Edinburgh University for that. And that really got me, there were two sides to it. One was the field work. So I was more or less living in the field area. So every weekend I'd go off and look at a different spot. And my intention at that time had been to get into field geology, but somehow events conspired, and I ended up more in the lab, so I had a lot of lab background. I crushed a lot of rocks in that time because when you're doing all these geochronological studies, you want to be sure that you're not contaminating anything, and you have to do it yourself. Went through a postdoc in Geneva looking at ophiolites in the Eastern Mediterranean,
Wow.
but decided at that time that academia was not really something I was really interested in. So I moved to Canada, and it was about 82, I think, and it was a terrible time to move here because all the geologists I met earlier had lost their jobs. It was the first real big downturn.
Oh,
But somehow I found something, and I ended up in using scanning electron microscopy, looking at mineralogy, which was really the foundations of some of these automated mineralogy systems. So that became kind of my, second area of expertise was mineralogy using automated equipment. And that really got me into the Ontario Geological Survey. So that was really a lot of fun. We built a fantastic lab in Sudbury, and we had all kinds of equipment. But the people thing was we lost a lot of people, and eventually I got asked to take over the lab management, and that was the fatal step that got me away from the technical side. And well, a couple of years later, I joined SGS, and ran the geochemistry lab in Toronto for about 10 years. And then when we purchased Lakefield, I had the opportunity to change. So I went back into mineralogy, ended up running Diamond Group services, which was a lot of fun. And my background, I understood all of the techniques, so I became something of more of a lab specialist. Did very little field work at that time and more lab management. But towards the end of my career with SGS, because of my expertise in geochemistry and mineralogy, I was kind of their technical lead to, answer client questions and find them methods. And I was working out of Lakefield, which is a metallurgical complex, so I got to understand the metallurgical side of things. Um, but ended up looking at a lot of new technologies. So in the last 3, 4 years, we looked at a variety of core scanning technologies, which was very
Yeah.
exciting, and gave a lot of presentations about that. But gradually it's taking hold. So it's been an interesting career. I don't think I've given a few talks to some of the young geologists, mentorship things on how your career develops, and it's really sometimes a lot of unexpected things come across your way, and you just jump at them. And
Yeah.
uh, but it's been really enjoyable. And these days, I do volunteer work with our local geological society, arranging talks, and also we have an incredible mineralogy department at the Royal Ontario Museum. So that's something I try and get involved with. Um,
That's brilliant. What an awesome journey. Like, yeah, so many adventures and unexpected twists and turns. That's like a really, really cool path that you ended up on.
yeah, with a lot expertise in a lot of different areas, the
Yeah.
geochemistry and the mineralogy side of things. So that's been a lot of fun. And, I get bored easily, so it's always fun to, go into a new area. Uh,
Yeah, definitely. I love that. I'm very curious what sort of pet rock you might have brought along for us today. I imagine you've seen all sorts of stuff in your career, so I'm very
yeah,
intrigued.
an interesting one, which is quite, can you see this?
Yeah, I'll just
Uh, it's a rock from the Kippawa alkaline complex in Quebec, and it is a rare earth bearing resource. So what you're seeing, the pink crystals there are eudialyte,
yeah.
and that's where a lot of the rare earths are contained. And in other parts of the complex, it's some very, very interesting mineralogy. So in a way, this expresses what I got interested in alkaline rocks fairly early on. And then, well, 2012 or thereabouts, started looking at rare earths from a mineralogical point of view using automated mineralogy. And, that group did a lot of work in this area. So this is an interesting rock that sort of encapsulates my interests in development, I guess, over the years. So the other minerals there are it's an amphibole of fedsonite and feldspar in there.
Wow. That is really cool. Well, thank you. Thank you for being here. Thank you for joining us. And yeah, I cannot wait to hear from you today. So thanks for taking the time to share. The screen's all looking good, so we can jump straight into it.
Okay, great. So I put this talk together. Originally, we had a, a short course in Vancouver on coarse gold. And that was when photon assay technology was just coming through, and people were really interested in it. I kind of grew, and based on the questions I had there was a lot of misunderstanding sometimes, or of what was the appropriate technique one would choose if you were measuring gold. So and not to make it too heavy, I kind of looked into the fire assay method, and in parts of my career, I was supervising fire assay labs, so I was heavily involved in it and building fire assay labs for clients later on with SGS. So fire assay, really interesting technique, and it's been around for a long time, and I think it's probably the oldest analytical method there is, because what we see is that there is evidence in some of the cuneiform tablets and so on in Troy and in central Anatolia that people were using a form fire assay as early as 2500 BC. And you have to understand, 3000 BC is when lead was discovered, or galena was discovered, and probably took experimentation over 500 years to come up with this lead fire assay method. So it has evolved. We don't know what the method was initially, but around 550 BC, there is evidence from Lydia that, and King Croesus's capital of Sardis, in the metallurgical complex, that they had a method of fire assay going there because they were able to refine the sample and separate the gold and silver and measure them separately, which led to the development of pure gold and pure silver coins. Later on, it developed in the Middle Ages when some of the Arab scientists started to develop mineral acids that were able to separate the gold from the silver, and the parting process evolved until when we see around 1550 AD, there's the method is more or less what we're using today. One thing they were using at that time is a balance to measure the amount of gold or silver, and you need a kind of standard. What was interesting, they used carob seed as the standard, and these were roughly 0.2 grams. In fact, our word carat comes from that. It's the weight of 1 carat of gold or 1 carat of diamond. Quite an interesting development, but that was their kind of, if you like, equivalent of a NIST standard, because nature was quite consistent in producing carob seeds of very consistent weights. Except, if you got them from a hermaphrodite tree, they were slightly smaller. You couldn't notice it with the naked eye, but unscrupulous merchants would use that, and so you might have less gold than you thought you had when you're settling a transaction. So, looking at Kingdom of Lydia, which is where some of this fire assay technology is documented, it's in Asia Minor, and Sardis is the capital of that kingdom. There's not very much left there because it was destroyed in the wars with the Persians, with the Romans, and so on. But you can see in the background there on the slide the Acropolis, where the fortress was and where King Croesus's forces were stationed. So that was their kind of fort that kept the city secure. We know of what happened at Sardis because of an incredible archaeological project which was carried out by Harvard and Cornell, and then later on they were joined by the British Museum, who excavated some of the rubbish tips, and they worked out, just by looking at what was discarded in there, what the method was used. They found that in this gold refinery complex, they had perfected the art of separating and refining gold and silver, and that was the basis of developing these pure gold and pure silver coins, and also mixtures in between. And that all depended on having a very good assay technique. So it's quite likely, they mixed it with the lead and separated the button off, and then they did what is known as a cementation process. So they mix salt and brick dust, various mixtures, and put it in a furnace. And what they were able to establish is that this oven or this furnace was only operated at 700 to 800 degrees. And at that temperature, the chlorine is liberated and it takes out the silver and leaves pure gold at the end. But even then, this was a very slow process. So it was not the only method of measuring gold. What they used was something called the touchstone method, which is actually a streak. So you take the object or the mineral which has the gold, or a coin which has the gold and silver, and use a streak, and you look at the color. So you have various mixtures, and you can compare it to your standard. So what was interesting about Sardis was there were rivers there where they had little black pebbles, which were ideal for developing streak plates for this touchstone method. So these two methods were the ones that happened at around 560 to 550 BC. And interestingly, they're still in use with the mints to this day. It was another 400 years before the specific gravity method came in when Archimedes developed it. But these three methods are still used. That's fire assay, touchstone, and specific gravity in many of the mints around the world. So King Croesus was an interesting character. His name is synonymous to this day with extreme wealth. He had so much gold that he had, cellars full of gold dust. And people say it's because there was a lot of gold in that area, but I think he must have perfected this separation of gold and silver and developed coinage. And once the coinage was available, it probably led to a lot of business development, and he profited from that. He splashed his wealth around, with all the oracles in various parts of Greece. Apparently, this is recorded by Herodotus 150 years later. He gave the oracle at Delphi 5 tons of gold, and some of that still existed 150 years later. But he was interested in prophecy for the future of his kingdom, and all she would say was that if he went to war, a great empire would be destroyed. So at that time, the Persians were invading his on the edges of his kingdom, and he decided to go to war with them, and he was defeated, I think, in the first battle. But instead of killing him, which was normally the fate of the leader of the defeated party, King Cyrus, the Persian king, made him a kind of business advisor and tutor to his son. So I reckon he must have had a lot of business experience that was responsible for his great wealth. And anyway, that's the start of coinage, because the Persians then took up that coinage and spread it around the ancient world. So jumping forward around 2,000 years, we see various developments in fire assay. There was a book written in around 1550 and published in 1556 by Agricola in Germany. And, he describes in one chapter the methods of fire assay. And it looks very much like the method we are using today, because by that time, as I said previously, the mineral acids were available. The alchemists were experimenting and developing all kinds of chemical methods. And so the fire assay method had developed to what it looks like today. But one point that he noted, and I think was really interested in, and it's just in this, that any assayer working on the assay needs to, close the door to the room where the assay furnace stands and concentrate on what he's doing, because it is a very, very complex process. And if you don't concentrate on what you're doing, you're going to make mistakes and create a lot of errors in your measurements. So that's something that is important to this day in fire assay. It is a very complex method. Here you see fire assay preparing the crucibles to which you've added the lead, you've added the sample, and you may put various additives depending on the composition of the sample, and you have to get that right, otherwise you will not get a good fire assay, and the concentration of gold or silver into the lead button will be affected. But the reason why the fire assay process has been so durable over these 3,000 years is it's a very good pre-concentration method. So you can take very low levels of gold, use this method to concentrate it up to levels where you can measure it easily. And that's essentially what happens here. You fire it up in a furnace, but there's a lot of problems sometimes in doing that because you're putting these crucibles in at high temperature, greater than 1,000 degrees, and you're not able to mark them. So you have to make sure that your handling procedures are able to figure out what sample is where. And that takes a lot of training of staff. So, most labs will have strict QA procedures to pre-label the bags, to mark corner crucibles so they know how the samples are laid out when they go into the furnace and when they come out of the furnace. And labs spend a lot of time in training of their staff. But there are also, several problems with doing gold by the fire assay method. Chiefly contamination from the flux that you're using, material from the furnace that could fall in if you're mixing high gold and low gold samples, and also contamination from previously used crucibles. So most labs will also have a tracking of each crucible to make sure that you're not cross-contaminating other samples. And these days, the majority of labs will have an ISO 17025 certification of the method itself. It's not the lab certification, it is a method. And that requires them to take part in all kinds of round-robin programs, having a good tracking system, and has to demonstrate that to auditors. So that's your best protection when you're selecting a lab for your program. And of course, you will need to put a variety of quality control samples in, just running to them quickly, like prep blanks, prep duplicates, pulp replicates, method blanks, and of course, certified reference materials in each batch of around 20 samples. This is what high volume commercial lab looks like these days, using these large furnaces, which take 84 crucibles of 30 grams in Canada, 50 crucibles, 50 grams in a lot of other places. And then using these multi-load, multi-pour systems, mechanized systems that pour 8 to 10 crucibles at a time. And you just have one observer here looking at it to make sure that the pours are properly completed. Then go through a cupellation process where the lead button that you create at this stage is heated so that the lead is absorbed, and you're left with the prill, the gold and silver prill, which is then parted using acid and run on either ICP OES or ICP-MS. So you can get easily measure down to 1 ppb detection limits using ICP-MS. Just an issue that comes up frequently is with gold properties is dealing with nuggety gold samples. And one thing that you see quite frequently as an instruction, if it's over 5 grams per ton or 10 grams per ton, re-assay the sample. But very often you see that the second result is lower than the first. And this is because there is a selection bias when you're dealing with gold particles. And it has been discussed by a couple of people like Linda Bloom and Moore Srivastava with the problem, because if you do that, with the selection bias working there, your overall values your resources might be lowered. So it's better to do random selected samples and do screen fire assays on them, or on at least 30 samples to figure out what the gold distribution is like. And currently we practice pulverized large samples of 1,000 grams when you've got a nuggety deposit, and sometimes even larger, and use 50-gram fire assay. But it's still been an issue using the fire assay process. One other way to tackle this is to look at gold deportment and ensure that use that mineralogical distribution. So what you see here is a QuemScan study of gold particles on the right-hand side, showing the distribution. And from that mineralogical constant, you can use Guy's equations to calculate what a representative sample size would be for that particular type of deposit. The other method that's also frequently used is screen gold metallics, where you screen the sample, take 1,500 to 1,000 grams and screen it at 140 mesh, then assay the entire plus fraction and two samples from the minus fraction. So then calculate a weighted average out of that data. Because of this multiple assays required for this method, it takes quite long, it's quite expensive. So it has always been a problem, doing this, you have to wait a long time for the results. So just looking at alternative gold methods, methods for gold were developed within the last century using aqua regia extraction and cyanide extraction. In places like Canada, aqua regia extraction is only used for soil samples, and here you see kind of the detection limits you get for that, something between 1 to 800 ppb, and sometimes sub ppb levels as well when you want greater sensitivity, particularly when you're doing soil geochemical surveys. Sample sizes can be 25 to 50 grams. So normally that is the method that is used in many soil geochemical surveys. A new method that has come along more recently is cold block, use of this cold block technology, which is essentially you put your sample in the test tube and you heat it with an infrared lamp to high energy. So it energizes the individual particles and promotes a very, very fast reaction. An Amira study done around 2018, 2019 showed that gold recoveries using these methods were very good. They were in the 98 to 100% recoveries. And this method is now used at a few mine sites, one in Western Canada and I think one in Australia, where there's a lot of copper in the ore, and it sort of affects the fire assay, so that they've used this method as a grade control method. And a couple of commercial labs like SGS and I think BV are starting to use this for other methods because it speeds up the digestion process. A new gold method that came out this year is one from ALS, which ALS calls gold nano 51. And it's interesting, it's a variant of aqua regia digestion, but what they do is they add some HF into it and use a pre-concentration step. So what the HF does is break down the silicates, and when you have encapsulated gold, it enables you to, say you have it in quartz, it'll dissolve the quartz and liberates the gold so that it's taken up the aqua regia. So it provides better precision than fire assay. So the finish here is by CPMS and with very low detection limits of 0.02 ppb, so 20 ppt in essence. And you can see this in this gold, how much lower they were able to get in this chart from ALS. It's one of the most sensitive methods out there. Comparing to cyanide leach, the problems with cyanide leach is not able to extract from all minerals, particularly when you have encapsulated gold. Another new method that came out, I think around 2018, 2019, is this method known as PPB gold, which was developed by Mel Linton. And essentially, it's a method that you can use out in the field. You take samples of 100 to 500 grams and mix them with a reagent. Don't tell you what the details of that reagent are. and they include a collection device in it, so known as the widget, and mix it for a day or so. That allows the gold to be liberated, to be extracted from the sample and captured on this widget. So I presume it's some type of ion exchange device. We don't know too much about that. This is then measured by EDXRF because having got rid of all the interferences that normally affect the gold lines in EDXRF, we were able to measure a pure gold line, and they're able to get this down to detection limits of around 20 ppb very rapidly. So you have your results back within a day or so and can operate it at your field cam. Looking at another gold method, which is quite popular, we look at this leach well accelerated cyanide leach for gold, which each tablet contains the cyanide and other oxidizing agents. So you can use it with very large samples, up to 2 kilos, and leaching happens within an hour, ensuring very quick dissolution of coarse gold. And you can use an AAS atomic absorption finish with detection limits of 0.01 ppm. And lower detection limits are possible if you use some type of solvent extraction like DIBK and ICP-MS finish. And you can measure a number of other elements. So these are the kind of detection limits that you can get with this type of extraction. They've also developed a pulverize and leach system. So it's using the same accelerated leach program, but you have a machine with 62 steel pots, and you mix it with 1.5 liters of water and grinding media. So you're pulverizing the sample and extracting the gold at the same time. So it reduces the time for gold analysis significantly for multiple samples. So if you're looking at a very fast method with a low capital outlay overall at a mine site, this is a system that has been deployed to a number of mine sites where they want very rapid gold analysis. Some of the leach well tests that we carried out on one project where we looked at the leach time at 2, 5, and 24 hours. It shows that average recovery in the 2-hour leach was close to 95%, and sometimes the recoveries were slightly higher than the fire assay values, which are in blue. 24-hour leaches did not actually improve the results, and may have led to some gold reabsorption. So you actually might get lower gold values for longer leaches. But it's important when you're using cyanide leaches to fire assay the residue to see how much gold might be in encapsulated gold. But it does give you a value that of recoverable gold, which is what is important in most mine sites. So in this next slide is a summary that was done by Simon Dominy in 2018, and just looks at the various methods: fire assay, screen fire assay, leach well, pulverize and leach, and the cost. So fire assay is one. Screen fire assay, which is a much more complex procedure, is much more expensive, as some of the other ones are. So the new technology, the photon assay, sort of in terms of cost, falls in just about the same as fire assay, but it has the advantages of the screen fire assay of using a much larger sample. So that's, we move on to looking at photon assay, or gamma, what is properly known as gamma activation analysis. So what this process does is uses a high energy photons at 8 MeV, which is an X-ray beam essentially, to produce a photonuclear excitation of sample nuclei, and was used by CSIRO to develop the photon assay system starting in 2001. So it was about 17 or 18 years to actually develop this process. So what happens is your X-ray beam excites the gold nucleus. It creates an isomer which has a half-life decay of 7.73 seconds. You don't have very long to measure that resulting gamma ray. You get an emission from this decay at 279 keV. And this is what it looks like on the excitation. You're exciting it to this level, and then it decays in 7 seconds back to its ground state. The physics of this was only worked out in the 1940s in Russia, and they developed it into an analytical method in the 1960s, and there were several installations of this gamma activation analysis at a number of mines in the former USSR, so in Uzbekistan and several gold mines in Russia. And the current system now derived from these developments is sold by Baltic Scientific in Latvia, and they call it the gold isomer industrial gold ore assay system, which has been certified for the EU. So just to compare this to some of the other methods for gold analysis, we can measure gold, the K line, using powerful X-ray excitation. So 160 kV X-ray tube generates high energy gold K lines that are free of the interferences that you see with some of the other lines, the L lines and M lines in gold. This method was developed by Anglo-American research in South Africa, and the system has a 0.3 ppm detection limit. So it's good for high-grade gold. It has a range of 0.5 to 500 grams per ton. These are numbers of samples that they can do. So when we had opened a lab in Red Lake in around 2000, and we were just overwhelmed because it was a very high grade mine. So you're looking at 20 to 40 ounces there, and we were just overwhelmed by by the rich gold samples that we were getting. Even the background was half an ounce when you swept up the dust in the lab. So we looked at systems like this, like XRF, to be able to cope with these very high level gold systems. But also looked at something like neutron activation, which was developed mainly by Eric Hoffman in the early 80s. So what it does, you're using a thermal neutron irradiation from a nuclear reactor that irradiates the gold atom and creates another isotope. So you go from gold 197 to gold 198. And that decays over a period of time with the gamma ray at 411.8 keV. But you have to wait about 7 days before interferences from other elements in there disappear, or before you can actually measure the gamma rays from the gold. So it took a relatively long time to carry this, but detection limits with this method were very good, and it was quite often used as a check method for fire assay methods. The fact that you could use 30-gram samples or even 50-gram samples meant that it was, the sampling statistics were better or similar to what was available when you did your fire assay. So looking at the photon assay procedure, this is the system that was developed by Cyro, and what it consists of, it's really off-the-shelf components. It has a linear accelerator here that irradiates the sample with this high-energy beam, and this is something that is widely available, used, for example, to look at baggage in airports to check the baggage out. And then it's using a standard high-purity germanium detector, which was used in neutron activation systems that have been around for a long time. But what needs to happen is once the sample is irradiated, you need to get it very quickly to the detector, because you only have 7 seconds before for the half-life. And the more counts that you can gather, the better is your precision in this process. So the sample is measured here, and my understanding these days that they do sort of 2 circuits for each sample to get detection limits that Chrysos has of around 12 ppb. So this is the system that is put together by Chrysos. It's 3 containers of irradiation and measuring systems with lead shielding to protect the users, the operators from the radiation. It takes only 10 minutes to perform the analysis, and the first deployments of the systems were in Western Australia, and then in Tanzania at the Barrick mine, and in Quebec with MSA. And currently there are 35 units installed around the world, and they have orders for up to 58 units. But the business model for Chrysos is quite different because the units are leased by the labs running the system, and they pay a fee per sample basis. Manufacture of these systems takes quite a long time, so I expect there's only about 15 to 18 units deployed annually. I think there were 29 units in mid-2024 and 35 units currently. But the one important fact with this Chrysos system is that you can use very large samples, so 400 to 500 gram samples are normal. Used, and you used a sealed plastic jar, which is purchased from Chrysos, and you put your reference materials in a separate jar and all your quality control samples in separate jars. And you can use coarsely crushed material, so you don't have to pulverize your sample. A -2 millimeter sample is all that is necessary, so it reduces the preparation time for the process. Analysis time is less than 2 minutes, and the whole process can be completed under 10 minutes. Jars can be handled after a couple of hours when the radiation has cooled to background levels. So detection limits quoted by Chrysos is around 0.12 grams per ton or 12 ppb, but the actual detection limits quoted by some of the commercial labs are nearer to 30 ppb. And detection limit, is quite important. So because really your data are quantitative at 10 times detection limit. So if you have a detection limit of 30 ppb, you're really looking at quantitative data at 300 ppb, and that's might work for mine projects where you have a reasonable amount of gold, but may not work in exploration projects where you would want to have detection limits, much lower detection limits of around 1 ppb or even lower, like this new ALS method, Nano 51. The calibration and QC is done by Chrysos using the synthetic and natural gold standards from Rock Labs and Aureus. And you can measure other elements, silver as well as copper, and sometimes lead and zinc. I think it would be mainly silver and copper that might be measured on some systems these days. This is a coarse gold study done by Chrysos when they were developing the system, and it just shows you the improved statistics you have when using a 500 gram sample versus fire assay. In this case, they use 25 gram samples, which is a lot of scatter. But that dispersion improves when you start to use 1 kilogram screen fire assay samples in the. So some of the advantages of the photon assay system is the very large sample size, and it's well suited for coarse gold analysis. And you can see that in a number of press releases and papers out there, and notably those by Nova Resources. One important thing is you're not going to lose gold in a pulverizer, because when you pulverize the sample, you get gold smeared out, and that can affect your results. The sample, this is a non-destructive analytical process. The whole sample is irradiated, and it's individual gold atoms that are irradiated. So it's matrix insensitive, and it doesn't. That's why you can use a fairly coarse sample. So it's got high sensitivity and rapid analysis in under 10 minutes. The problem that we've had with the fire assay process, complex process, takes a lot of people, and so it takes a lot of time. So, leading up to the introduction for assay, we saw labs having turnaround times of 2 or 3 months and longer. And I think that created a lot of dissatisfaction in the exploration community. So that the community was looking for faster methods, and that's led to certainly photon assay and even systems like PPB Gold that give you data in the field. The comparisons done, there's a lot of testing carried out by Chrysos, and the comparisons that they've shown between photon assay and fire assay good, but there's a lot of variability on the fire assay side when you're comparing 50-gram sample fire assays to 500-gram samples for photon assay. There are, of course, like with every analytical technique, there are some issues that can cause problems. So one of them is a self-shielding effect, so that if you have very coarse gold, not all of the gamma rays make it out to the detector, and that might reduce the amount of gold that you measure in the sample. This effect has not been quantified, but it could be 3 to 5%, according to some papers out there. It is also not able to process samples with significant amount of uranium and thorium because of their radioactivity. And when you have significant amounts of barium greater than 1,000 ppm or lead greater than 2%, that creates interferences also that cannot be resolved. And as time goes on, we'll as with every technique, we'll understand better what problems can happen when you're carrying out a photon assay. Another thing is, if you're trying to do additional elements like copper, it requires high radiation energies, which might affect your tube life. But there's quite a large number of elements that could be measured by the system, but those are all under development by Chrysos, or being reviewed by Chrysos at the moment. The key one is gold, but as mentioned previously, you can measure silver, copper, and lead, and some other rare earths and so on. Potentially, Chrysos is going to try and develop the system to measure these elements. Here we see the deployment currently for 2025, mainly in Australia, of course, in East and West Africa, and also in North America. There's about 35 units deployed, and there's quite a number that are going to be coming into North America. We've had a number of new, in addition to the standard commercial labs like SGS, ALS, and BV, we've had a couple of new entrants in this area with MSA labs putting in a lot of systems, and Britannia Mining Services, which is planning to put 10 photon assay systems within North America. And we've seen it deployed by Barrick at their mine site in Nevada, at the Nevada gold area. So they're moving over all of their gold analysis systems to photon assay. It's also quite heavily used in West Africa and in some of the Tanzanian gold mines. And of course, in Australia, in Kalgoorlie. This data on the right-hand side is from in 2003. So as the number of units deployed out there goes up, utilization is starting to drop a bit. And also, I think this coincided with a slowdown in gold exploration, which might have affected the volumes going through the photon assay systems. But looking at the quarterly photon assay samples analyzed, you can see it has grown every quarter, and it's growing at mine sites. The samples in blue, so it's about 1.1 million from commercial labs and over 500,000 from mine site labs. And the goals of Chrysos is to expand deployment of the photon assay system to most of the mine site labs. So this is an example of commercial labs working with the photon assay system, Intertek, ALS, MSA, SGS, and some of the mining companies also working with photon assay. The latest who've signed on was Newmont. They just signed a master services agreement with Newmont and putting out the first photon assay system in one of their Ghana mines. So the technique is really sort of starting to push into the fire assay space. I reckon there's about maybe close to 60 million samples in total for gold, maybe more. At the moment, photon assay's got about 10% of that. So there's lots of room to grow. But obviously, it's not going to replace every sample sent for gold determination, particularly when you're interested in very low detection limits. So one question that that's come up fairly frequently is, this is a new technique. Is it accepted when you're putting out a report there under a system like 43101 or JORC? And there's an interesting response to that from Simon Dominy on, I think it's on LinkedIn, on one of the Chrysos posts, which states basically you have to do your check work as long as you have confidence in the technique. Do the proper check work to validate the data that might be done by photon assay. And there are a number of different ways you can do this, because as the technique is non-destructive, you can take your 500-gram material. You can use a fire assay to extinction, the fire assay the entire sample. You can do a screen fire assay on it, or you could do a leach well type process with the fire assay of the residue to estimate what the gold is as a check on that sample. But just note, because some of these procedures have multiple steps and there's an error associated with each one that is additive. So the overall error in the check procedures might be higher than with the GAA process. There have been a couple of interesting papers, if you're looking for some background on this, which came out within the last year from Simon Dominy. This paper looks at various aspects of application of photon assay to coarse gold mineralization, and particularly if you're changing methods sort of mid-course, you might, say switch from screen fire assay, which may be a very expensive process, and moving on to photon assay. What is it that the QP needs to do to check that you're getting data that is equivalent? And also another paper that he published last year, which looks at comparison of all these various techniques discussed here: fire assay, screen fire assay, photon assay, and also the PPB gold method. Okay, I think just to conclude, obviously, using all these various systems, the most important part of using them is ensuring that your samples are prepared correctly, and that still is a key factor in reducing error when dealing with gold assay systems, no matter what method is used. Gold by fire assay is still the mainstay of exploration and mining industry, but it's gradually being replaced by photon assay, particularly at mine sites. But where you want low detection limits of 1 ppb, it's still going to be an important method. Um, Accelerated cyanide leaches have a role to play because it is a lot cheaper to set up a system to do this. It's you may be looking at, I would say, $300,000-400,000 versus $3 to $4 million for a photon assay system. So if you're looking at a low-cost system that gives you most of the data you want, you might look at accelerated cyanide leaches or even the cold block technology, which is very cheap to set up. But the commercialization of disruptive technology like photon assay, I think will benefit the coarse gold projects. And, that's a lot of mines out there and reduces the sampling and assaying errors. And also the big benefit of fast turnaround times, which has been a real problem within the industry. But it also is going to have an impact on the business models of current laboratories because of the model that is set up by Chrysos, where they lease the system out, and there is a fixed charge for fixed number of samples per month. So the revenues for gold from some of the commercial labs might be reduced, and that might have impact on their other services. That's going to be interesting to see over the next year or so, or year or two, because particularly in North America, we have like 20 new labs slated to come on stream. And that's going to create a lot of capacity. And usually when we have a lot of capacity, it creates a business problem. That's it, and happy to hear your questions on this.
Thank you so much, Hugh. That was super informative. I really appreciate you taking the time to go through that.